There we go. All right. Hey, everybody. I got 2 whole viewers right now. I realize it's 9:50. Oh, everyone's gone. All right, whatever. So I'm going to talk about the refrigeration cycle. Um, a smidge of physics, but it's summer, and I always talk about car stuff. But it's summer, so what car-related thing can I talk about? Let's talk about how your AC works in your car. And a lot of people don't understand how it works, and I figured that I could take this opportunity to share with everybody how your AC system works. On the left, I have pressure and enthalpy, but I'm going to just come back to that later. Right now, we're going to start off way more basic than that. Um, right now, we're going to start off with the components of your AC system, right? So let me get my little drawing brush out. Oopsie. There we go. So the typical air conditioner system is composed of 4 primary components. The first one that everyone knows about is the compressor. There's a couple different types of compressors that are used. There's a scroll type, there's a screw type, there's centrifugal compressors, etc. I just shaped it kind of like a turbo, poorly, but like a turbo because that's what you guys are used to seeing for compressors. Then there is the condenser. After the condenser is a TXV or an orifice. Basically, it is a expansion device. And then that goes to the evaporator, which goes back to the compressor. Now, in this system, we have a liquid. We have liquid. Apparently liquid spelled with an E. We have thank you OneNote. Check that out. That was awesome. All right, let's go back to that again. Sorry about that. That's the longest queue ever. We have a liquid, and we have a vapor. We have a high pressure side, and we have a low pressure side. And then we just have hot and cold. All right, so in this cycle, with these 4 steps, we have all of these situations going on. And each one is really important in this cycle. So what exactly are we doing? Well, what we're doing is we're taking a refrigerant, which has a very low boiling temperature. Sorry, YouTube just popped up a thing telling me that something's wrong with my stream. I thought this was going to work well, but apparently not. Okay, well, thank you. Thank you, YouTube, for that. Yeah, I have no idea what it's asking for. It says that my keyframe frequency, which I'm pretty sure is the authentication frequency, how often it's authenticating, it says it isn't fast enough. And so it's creating buffering issues for other people watching through the stream, which I can imagine would be frustrating as hell to have that happen. I apologize if that's happening to you. I'm going to crank the bit rate up a bunch and see if that helps any. I don't have anything on here that says anything about a key frequency, so oops. Anyways, back to what I was talking about with one person. Hello, that one person. Anyways, okay, so what we're doing is we're taking a refrigerant which has a low boiling temperature. Now that's really key, right? If you look at things like carbon dioxide or liquid nitrogen and things like that, those things have very, very low boiling temperatures. And so when you put them in contact with something above that, what do you get? You get a phase change, right? So if I take the liquid nitrogen as a liquid and I pour it into the atmosphere is warm and at a low pressure, and then that liquid becomes a vapor. Now, the reason liquid nitrogen makes things so darn cold is that when it becomes a vapor, it takes the heat with it, right? And that's called latent heat of vaporization. So the amount of heat that it takes to create that vapor is transferred into the vapor and away from the source. So in the case of a refrigerator, for example, the warmth inside the refrigerator, relative warmth, is the heat source. And so if I feed a refrigerant into that heat source, then it will vaporize. And when it does that, it absorbs heat and then takes it with it. And so what I can do is I can say my evaporator here, my evaporator is in a warm area, right? So I have heat going into my evaporator. And if I feed it some really cold refrigerant, it interfaces in the evaporator and it leaves. Oops, I went the wrong way. Sorry. Let me fix my cycle. I'm going this way. So I feed it some cold refrigerant and it goes into the evaporator, and then heat transfer occurs and the refrigerant becomes hot. Okay? So you see the heat going into the evaporator but not coming out into the atmosphere. It goes into the refrigerant. And so what that means is that I get cold, oops, I get cold leaving the evaporator, and that's what cools off the area where I'm at, right? Okay, so, but what about this refrigerant? Like, there's some key things to this refrigerant. We're not just taking refrigerant and saying, hey, let's make it cold, because this refrigerant has to undergo that phase change. Right? I talked about that phase change for latent heat of vaporization to occur, to transfer. So if I need that phase change to occur, then I have to do certain things. One of them is I need it first to be a vapor. I'm sorry, a liquid. Why do I keep doing that? I don't understand. So I need it to be a liquid initially. Because if it's already a vapor, the phase change is not going to occur. It's not going to absorb near as much heat. So I need to be a liquid, but I need that phase change to occur in the evaporator. Now, what that means is I need to strategically place the pressure of this liquid and the temperature of this liquid so that when it hits this evaporator, this change occurs. Well, the temperature of the liquid is semi-adjustable via the condenser. That's where the heat ends up going in the long run. But the pressure is calibrated by this orifice here, this TXV. Now, what's really interesting about this is in the old days, it was just an orifice, and it literally was just a pipe with a plate with a hole in it connected to another pipe. And the gas would flow through, and then there's this restriction in the orifice, and based on the flow rate and the temperature, you would get a pressure drop through an orifice. And so you would have high pressure here and low pressure here. But that wasn't very, it wasn't ideal, because if the heat load was too low, what you could get is you could have this liquid carry on, I went that way, this liquid carry through the evaporator into the condenser or the compressor, and then you're trying to compress a liquid with a compressor, and if it's a positive displacement compressor, then things go breaky, and we don't want that at all. So we don't want any liquid in the compressor. So the TXV was invented to monitor the temperature, I believe it's on this leg here, and based on the temperature of that leg, which gives you an idea of the heat load coming through the evaporator, it can change the size of the orifice in here. TXV is a thermo expansion valve, I believe. And it changes the bypass rate through this thing here, which changes the pressure. So it knows that based on this temperature, if I want this to be a vapor, then I need a specific pressure, in this leg right here, in order for the phase change to occur in the evaporator. So I realize I'm kind of going backwards to the cycle, but it's a cycle, it's a loop, so it's hard to pick a point, to start from. So I like to start from, where you're experiencing the heat
in your car, and you crank on your AC, like, please cool down, right? Well, when the system's not running at all, the compressor's not running, there's no flow in the system. If there's no flow through the system, then there's no pressure drop across TXV, so the pressure just equalizes in the system. And so it's usually going to be down like, 20, 30 psi, something like that. And then the compressor kicks on. Oh, it's 20, 30 psi, and it's all pretty much a vapor at that point. Then the compressor kicks on. What does the compressor do? Well, it takes that vapor and it starts to push it through the system. Okay, as a flow picks up, then this orifice here, the TXV, is shutting down, providing the most restriction possible in this line at this point. So then that compressor starts to literally do its job, compress, right? Compress that vapor into a high enough pressure that it's going to want to become a liquid again. But the compressors, just like your turbocharger in your car or your air compressor at home or anything, they add energy, they add heat to it. So the heat level leaving this compressor is actually really high. There's a lot of heat in here. And we got to get rid of that heat if we want this to become a liquid. So what we have here is we have a high pressure vapor, high temperature, sorry, high pressure, high temperature vapor. And then it hits the condenser, and the condenser goes bleh, and pukes all the heat off to the atmosphere, which is in the front of your car or it's behind your house. Your compressor and your condenser are in the same location. Boy, OneNote is just giving me hell today, isn't it? Um, then it leaves the condenser cooled off. So then I have here, I still have a high pressure, but now I have a low temperature and it's a liquid, right? So this high pressure, low temperature liquid now is traveling towards this orifice. And like I said before, the job of this orifice is to reduce the pressure appropriately so that the phase change occurs in the evaporator. So what it does is, again, it restricts the flow through here and allows the liquid to drop in pressure on this side so that when it hits the evaporator, the addition of heat from the car or from your house or whatever is enough to undergo that phase change. And when it undergoes that phase change, again, latent heat of vaporization is absorbed by your heat source and put into the system here. So here on this side, I forgot to mention, this is a low pressure, low temperature liquid. On this side, top left, we have a high temperature, low pressure vapor. So you have phase changes occurring in the evaporator and the condenser. You have pressure changes occurring in the compressor and the TXV. And then temperature changes occur at various points in here. Again, the compressor adds heat, condenser removes it. TXV doesn't really affect the temperature much, although if you think about any time you let something expand, it tends to absorb a little bit of heat, but it feels cold. You feel like you feel it cold like on your hand. It's pulling the heat out of your hand. And then it's the evaporator and it absorbs heat again and becomes a higher temperature. This is the highest temperature and the highest pressure in the system. And let's see, what else should I say about that? I guess that's really it. So what does that mean for your car? Well, it means a couple things. One, for an AC to work, right? You need somewhere for that heat to go. The heat's got to go somewhere, right? You have this source of heat in the car, and you got to take that heat from inside the car, and you got to put it outside the car. And this is the means of which you do it, but it's got to be able to be removed from the car. So if you stick your front mount intercooler in front of your condenser, you're going to impact the ability of your AC system to work because you got the airflow being restricted across the condenser, and you're not going to get as much heat out, so your AC is not going to work quite as good. Most people don't really ever notice much of a difference on that, but in really, really hot climates, it can become an issue for sure. Just like your radiator. If you stick your front mount intercooler in front of your condenser, which is in front of your radiator, then you can have issues where you don't have enough cooling to keep the engine cool and all that. Because this gets hot. I mean, it's a source of heat. So now my radiator, instead of seeing atmospheric temperature air, it's seeing 100 something degree air on the front of it. Well, it's not going to pull a lot of heat out of the coolant if I'm feeding a bunch of hot air in front of it. And then add in, I have my intercooler, then my condenser, and then my radiator, right? Source of heat, source of heat, source of heat, right? This radiator, we want it to be all super efficient. We want to get our bigger, gigantic, aluminum radiator or whatever we're going to run and hope that it helps a whole bunch. But it's only going to be as good as the amount of heat transfer that's available to it. So if you heat it up here, you heat it up here, and you get to your radiator, you're not going to have as good cooling. A little bit of a tangent, but hey, that works. I don't have any questions lined up. Anybody got any questions? I see the chat is empty. Does the chat even work? Hello? Okay, that posted up. Cool. Okay, so what's this diagram on the left? Well, this diagram on the left is pressure. Lost the ability to write. Pressure and enthalpy. So each of the cycles of the refrigeration cycle fall onto this graph, and they give you an idea of what is going on. W here, W stands for work. Q is heat. So what we're doing here is we're adding work to the system, which is what causes the pressure to rise. Okay, so we're adding work to the system, and that is done with the compressor. And if you think about your car, that's attached to your crankshaft and via a belt, and that's pulling energy directly out of the engine. So you're using horsepower from the engine to compress the air and travel up this pressure enthalpy graph. Typically these are pressure volume, but this one is focused around enthalpy because they're really going heavy on the Q, and they're going heavy on what happens during the phase change in this graph. Thanks for the tangent. Hey, buddy. Cycling switches for the high side. ND. What's ND? Anyways, let me know. Okay, so I have the compression, condensation. So if you look at this cycle here, just like it says, we got compression, then we have condensation. We're removing Q. See that right there? The Q, that's heat leaving the system, and the center here is your engine or your system. So we're condensing. Pressure is constant through that phase, just like we see here. The compressor goes through the condenser and then to the TXP, and that's where expansion occurs. So we just follow this graph here to the left, whoop, like that. And that's our condensation. That's removal of heat, constant pressure. We've lost enthalpy. And then we're going to go into the expansion valve. And the expansion valve, like I said before, lowers the pressure. And then it goes straight down here. Lowers the pressure. Like that. And then we are going to go into the evaporator. Pressure again being constant as it travels to the left side of this loop here. And it goes to the evaporator and it goes a phase change, absorbs a lot of Q. Q being heat or heat energy. And then we're back to the compressor again. Now the Q and the Q here represent the heat going into the system from the inside of your car, the inside of your house, whatever it is. And then this is the heat leaving the system via the condenser from the front of the car or out through your backyard. And you guys have seen the condensers in the backyard, right? You got the box outside in the back. It's got all the grating on the side because it's got the condenser, fins all in here, and there's a big fan on top. The fan is blowing the heat out. It's drawing in atmospheric air and blowing out the heat like that. So you have the fan moving air across your condenser, but if you look inside, you get a little X-ray vision in here. What you'll see is inside there's a little compressor in the middle, sitting there by itself. Sometimes they're tall and skinny if they're scroll types, and then sometimes they're flat and round like this if it's like a centrifugal style or a piston. Often there's not a whole lot of centrifugal AC compressors. I said that earlier, but I meant piston style. There's reciprocating pistons, and then there's the scroll or screw types like a supercharger. A lot of these vertical ones like that, and these guys are in here doing the compression of your fluid. So, but you gotta look past that fan because that fan is only a small part of the whole function. It's just moving the air across your condenser coils. Just like when you're driving your car down the road, the speed of the car and the air is moving through your condenser on the road. That's what that little fan's doing. There, now it's even. I'm sure the OCD guys are seeing my uneven fan going, ah! Low side pressures. Curious if you demonstrate variable displacement compressors. I mean, for like home stuff, are you talking like the Waterbury pumps, for example? I'm not sure that's what he's talking about. So if you wanted to, instead of just controlling your pressure based on action of the TXV, You could also change your compressor um, ratio, your compression ratio, essentially. And so I think I've never seen the Waterburys before. That might be what he's talking about, the Waterbury pump. It's a bunch of pistons on a plate, and I should do a search, but the plate oscillates, and these pistons move in cylinders, and the plate oscillates, and so the pistons move up and down inside the cylinder, and they have little valves, little orifices in them, and it draws in fluid and compresses it and pushes it out. Some of them, it's all on the top, and there's just check valves, one-way check valves. One draws air in, or vapor in, one draws vapor out. And so if I alter the position of this plate or the angle of this plate, I can cause the pistons to move a further distance than they did before. So that's one way you can have a piston compressor that's a variable compression. I don't know, is that what you're talking about? Okay, right on, William. Not the greatest drawing, I get it, but if you look at Waterbury pumps, they're actually kind of neat. Um, uh, Almost every um, automotive compressor for air conditioning is a Waterbury style, and if you take them apart, it's really neat to see the little plate with the many little connecting rods and the and the pistons. They're kind of fun to play with too. And you might go to a junkyard and see someone's got some little thing with these pistons on the legs. Man, I did it again. Yeah, today one note's kicking my ass. Um, they have these little sculptures where they make with all the stuff that falls out of the cars and they weld things together. Well, the one that you see that's got the circle and the little legs, it looks like pistons, for legs. That's a water pump that they had taken apart. Um, I might be able to attach one actually right here into. Let me do that really quick. Yeah, let's do that. That'd be cool. Waterbury pump. Images. So I'm on the Googs right now. So here's the guts of one. Let me copy this guy right here. Here's one of them. That's the wrong window. Here we go. So this here, you see that there's all those cylinders that the pistons here ride inside, and then there's this looks like the rotational part for the ports for ingesting and expelling the air, and then this looks like the plate that holds all the rods for the water valve. This isn't the most common style. This is one that's actually for a hydraulic system, but it was a quick one that I found really quick. I said quick a lot of times. So essentially, if we look, oh, here we go. Copy. Let's go back over here again. So if I paste this guy here, this is a variable displacement one. And let's see if I can get it bigger. Does it want to go bigger? As big as I want it to go. Why? There we go. So here's that plate that the pistons ride on I was talking about. And so if I change the angle, so if I take this ball right here, for example, if I was to swing this over vertical, then the difference from this point to the point down here would be very low. And if I swing this over and angle this plate very steeply, then you'd see that the piston would travel the most up the cylinder and the most down the cylinder here. And so that's a variable displacement piston pump or Waterbury pump or compressor or whatever you want to use it for. It might be interesting to do an engine with one of those actually. That'd be pretty cool because you could do variable compression with an engine. I'm sure someone's done it and tried, and who knows how well they did. And so this here shows the inlet and outlet of this is basically your valves and your camshaft. So the shape of this port would be like a camshaft. If I had a big fat opening and then it goes skinny for some weird reason, that'd be like having a fast opening camshaft. And you come across this port and all of a sudden, boom, it fills with air really fast. Or if I had it fat in the middle, it'd be like having a lot of lift on a cam or something. So like this shape kind of simulates a camshaft profile. And then this is the discharge side, and the red being the high pressure. And you can see here the red coincides with high pressure because the piston is squished the volume, and you have that there. Anyway, so that's a variable compression pump. Let me go back to my other page. And then what did you mean? Graham gingerbread STI no drop. What was that? What's that question? So maybe I can help out answer that. I don't know what you meant by no drop. All right. So now we're back to this again. Oh, gotcha. ND no drop. All right. Cycling switches for high side no drop. So AVCS for a compressor, no VTEC or AVCS. AVCS for a compressor. I'm contemplating. Maybe I would say more like VTEC. Because with the VTEC, we're adjusting the lift, the total travel of the valve in that case, just like you would be in the variable compressor. Whereas AVCS, you're only changing the timing. So if it was AVCS, all we'd be doing is spinning that little, we'd be spinning that disc to the right or to the left, and that would give us the variable timing. But that wouldn't really do much for us. I mean, I guess you could technically, that would work really well too, because I could push some of what I've compressed back out again. So I suppose that that is absolutely a viable way of doing it. Yeah, exactly. And so in the if I change the angle of that plate and I've altered the max high and low, then that's kind of like having VTEC 'cause I've changed the swing of the piston or the valve in the case of the engine. Um, Whereas AVCS only changes the timing. The lift and duration is always the same with AVCS. It's just the center line of the cam has changed. Where VTEC, you get a different lift and different duration when it activates. But with the variable compression pump, it's variable in between there. So it isn't just a high and a low. It's adjustable in that range. So it's more like the BMW's Valvetronic system where it can do variable everything and in that. A line tech. What's a line tech? Because to me, a line tech sounds like you work at a restaurant. Oh, okay. Gotcha. So almost like flat rate kind of stuff. Do you flat rate work or do you are you paid hourly? Oh, okay. Interesting. So that's actually something that I want to talk about. I'm looking for a new tech at the shop, someone who's wants to kind of apprentice and learn more stuff. I like factory trained techs. Um, Fiat or flat? Oh, flat rate, right on. Yeah, yeah. So I like factory trained techs because they get a lot of the in depth as far as like what's located where and how some of the stuff works, but they're not trained well in troubleshooting and they're not trained well in understanding how all the parts integrate with each other. And so I like to get a factory tech who has done the factory training where they say, if you have this problem, go to this step, and read the troubleshooting guide and tells you to check the resistance from pin B52 to connector, E36 and see if the resistance is within a certain range, right? Well, they're not teaching you anything about the system. When you do that, you're just following this troubleshooting guide. And so I like getting you guys when you're like, well, I just follow this guide, right, or whatever, and then I'm like saying, okay, well, let's back it up. Where's E36? What's that? And then what is that? What is that attached to? And I like to break it all down and get you guys to see better how each component affects its neighboring components and how the signal travels through, a circuit or whether it be mechanical signal from your foot on a master cylinder or whatever. And then I like to take you guys and really break you down in that regard so you see better interaction of how things go. And what I tend to find is guys that are stuck in the book, they need it to troubleshoot. start keeping it in the toolbox. They don't need it as much. And I don't want it to where you don't need it ever, and I want you to definitely reference it. But I like to see when you guys have a better idea of how things work. So someone sends me an email and they're like, "Hey Dom, I have this problem," and I'm going through, okay, what are all the things that can cause that problem? And I don't know all those things because I've experienced all those problems, but because I understand how each system affects it. Or I think about, okay, well, this sounds like it's rich. Well, is it because there's a feedback cycle that's telling it to inappropriately go rich? Is it rich because there's a mechanical issue that's causing more fuel pressure? Is it rich because I have a short on an injector lead that's causing it to stick open? Is it rich for, because there's an air leak and the air leak is telling the mass airflow sensor that there's more air than there really is going into the engine? So understanding how everything works together is great. So the first thing when you have a problem and you get a check engine light, it says camshaft too advanced. Well, what does that mean? And Bill, you look at what the book says, and it says that after so many cycles, it shows that the camshaft position is outside of this delta from target, whether it be 10 degrees or whatever, right? And then you go, okay, well, is that true? That's the first step. Is it true? Is that signal even correct? Is the ECU responding to an inappropriate signal, or is it responding to an actual inappropriate condition, right? And so you have to think about, okay, so one, what creates that signal? And is the signal right? Yeah, well, yeah, it often is for sure. But on the Subaru, it's often mechanical too. Um, So, I have to look at first off, great. Well, the book will say, oh, well, check this, check the oil, check whatever, and the book almost always assumes that the check engine light condition actually exists. Oh, well, if it says that it's over advanced, that's because it is. They rarely ever have a situation where it says, well, this is actually advanced. Verify that's advanced. Do this procedure and see if the signal responds as it should. So if I had a camshaft over advanced, in a Subaru, for example, because the AVCS or whatever, I short the AVCS solenoid out. I give it a full 100% signal for a second. Bam, and I watch and see if the reading responds as it should, and that tells me, hey, the system, the oil system is functioning correctly. I short the AVCS solenoid, the full open, bam, the freaking the cam went full advanced. Well, it's cool. It tells me the oil system works. It tells me the gear's functioning properly. So now, is the solenoid just not functioning properly? Well, it might not be. Even though it responded to a full open signal, it could be partially clogged, and the in-between positions is not getting good oil flow or whatever. So then I say, well, I know that the cam gears work. I know the cam is advanced. I know the sensor's working properly. So therefore, I did have a situation where my camshaft was over advanced for a period of time, and then I can go in and change the valve or do whatever I need to do to continue the troubleshooting. So it's important to me that the guys have a good understanding of how the systems tie together. Um, but at the same time, I like when they have a base knowledge of how the systems work in the first place, and that's always super handy. The lids. See, to me, because I'm old, lid is referring to marijuana, a quantity of marijuana. So, what is the lids?
What is lid? What?
Hey, Ryan. The PIDs. Oh, the PIDs. Yes. Yeah. Could you guys hear my friend Ryan? I'm on Discord right now, while I'm doing this video here. Say hi, Ryan.
Hi.
Yep. You're coming through. I see my desktop audio bar just scream across the screen, so you're live on YouTube. Yeah, the PIDs, right? What's funny is in the aftermarket world, we rarely say PID unless it's aftermarket domestic. Um, the Chevy guys and the Ford guys, they say PID all day long, but I fucking almost never hear anyone with a Subaru ever say PID, which is interesting, I guess. I don't know. For me, it's parameter. I just say the parameter, or if I'm taking a log, I see what parameter I'm logging, etc. Okay, so I just did the refrigeration cycle. Is there any questions about that in particular? Dealership. The dealership? Yeah, well, they always talk about PIDs because that's the technical, factory term and all that stuff. I don't, PID, the PID hurts my ears. I don't like hearing it. First time someone says PIDs, I'm like, ugh, ugh, ugh. I don't like it. 16-bit. What's 16-bit? Communication protocol or the ECM? Like O2 to O5 WRX is a 16-bit ECU. You're talking in that kind of 16-bit? Let's see. All right, what else can I say? Okay, so we talked about the TXV, talked about before and after. Before we're just using the orifice, or now using the valve that senses temperature over here. We talked about the condenser. We talked a little bit about the construction of the condenser. Talked about the compressor, talked about different types of compressors and what his job is. We talked about the evaporator. Um, and we talked about everything in here: high pressure, vapor, liquid, and yeah, liquid vapor. I think that's it. Let's see. I need to work for you. DM me. Do you live in the area? 2017 Ford F-150 is still fucking 16-bit. Hey man, thanks Wayne. Thanks for coming out. I say coming out. I mean, thanks for watching me on your phone or laptop, whatever you're doing. Appreciate it. 2017 Ford F-150 is still 16-bit, huh? Well, I mean, I guess that makes sense, right? They don't have a lot of jobs to do. Unless you're talking about the EcoBoost. If the EcoBoost 16-bit, I'd be really surprised. Because typically the more tasks, the stronger the processing power you need. When you're controlling boost and you're controlling valve timing, you're controlling a drive-by-wire throttle body, and you're interfacing with the body control module, and you have CAN bus communications with your ABS system, and your vehicle damage control systems and all that kind of stuff. Typically, 16-bit ECMs don't carry enough oomph to do all those parallel calculations and communications. Really interested if that was the EcoBoost as well. What's my stream delay on this thing? Is it instant? I do not have a stream delay set up, so that's good. Thanks for the Sonar for cooling mod. EcoBoost 16-bit. Wow, that surprises me a bunch. Because they have freaking 4 cams with variable timing. And then boost control system on 2 turbos. Drive-by-wire. That's really surprising me that it's still 16-bit. What if it has just more parallel processors and stuff instead of just like a single processor or what to handle the load? I wonder how they divide the load, really, is my question. Yeah. Well, good. Everybody else is 32-bit since like '05. All the Subarus that drive-by-wire are 32-bit. When they added drive-by-wire, they went 32-bit. They had AVCS at 16 back in the age of 20 in 2007. But in the US, there's no 16-bit AVCS cars and no 16-bit drive-by-wire cars. In Subarus, again, like I said. This is some laggy stuff. Alright, man. Well, thanks for coming out. I'm going to stop this video because I talked about the refrigeration cycle and there's no other questions. I think I covered everything I wanted to cover. Yeah, I think I did. So thanks again. Thanks for coming out. If you want to shoot the breeze some more, hit me up on Facebook or something or Discord or some shit. Other than that, have a good night. Thanks for coming out, guys.